The photoelectric effect is a phenomenon where electrons are ejected from the surface of a material, usually a metal, when light of a certain frequency shines on it. This effect puzzled scientists in the late 19th and early 20th centuries because it didn't fit with classical wave theories of light. Classical theory predicted that increasing the intensity of light, regardless of its frequency, should supply enough energy to release electrons from a metal surface. However, experiments showed otherwise. No electrons were emitted unless the light had a frequency above a certain threshold, no matter how intense the light was. Additionally, electrons were ejected instantly, with no delay. In 1905, Albert Einstein explained the photoelectric effect using quantum theory, building on Max Planck's idea that light is made of energy packets, or photons. Einstein proposed that each photon has energy E equals hf, where h is Planck's constant and f is the light frequency. An electron is ejected only if a photon has enough energy to overcome the work function, the minimum energy needed to free the electron, of the material. If the photon has more energy than the work function, the extra energy becomes the kinetic energy of the ejected electron. This theory explained why no electrons are emitted below a certain frequency, regardless of intensity. Increasing light intensity increases the number of emitted electrons if frequency is above the threshold, but not their energy. Increasing the frequency increases the kinetic energy of the emitted electrons. Graphs: kinetic energy versus frequency, a straight line graph starting at the threshold frequency. The slope is Planck's constant, and the y-intercept is negative, equal to the negative work function. Electron current versus light intensity, a linear relationship, assuming frequency is above the threshold, showing that more light results in more electrons ejected. Kinetic energy versus light intensity, a flat line, showing that intensity doesn't affect energy per electron. Modern uses of the photoelectric effect: solar cells convert sunlight into electricity using photovoltaic materials. Light sensors, used in automatic doors, alarms, and brightness detection. Photomultiplier tubes, detect faint light in scientific instruments. Digital cameras, use photoelectric sensors to capture light and form images. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921 and helped establish quantum physics.